his work.
Okay.
Good afternoon, everyone. So today we have Professor Ivan Arraut. He's an assistant professor at the University of St. Joseph in Macau. And today he was doing his PhD in Japan. And today he's gonna be talking about the problem of dark matter and dark energy. So welcome to our university, to our center. Thank you very much.
Okay. Thank you. Thanks for the introduction. Yeah, my name is Ivan Arraut. I graduated from Osaka University, 2014 actually. I had some JSPS postdoctoral position in Tokyo after, and in between, before that, a CIS PIFI program in Beijing, in ITP.
IZDP.
Well, there is a Carlif something, and there's one which is not Carlif, but I think they are the same.
Oh, no, they're not the same.
They are not the same, okay, they are split away.
Yeah,
I was, I don't know in which one I was, but I was in one of them.
Okay.
Then, I come from, I am in Macau, based in Macau, University of St. Joseph. I have been there the last 3 years. Their physics is just starting. It's a baby in this university. I am introducing it. And I come to talk about dark matter and dark energy. I don't know if you are familiar with the problem, but I will explain it slowly, step by step. They are different. Dark matter and dark energy is different, but sometimes the students, when in the early stage of career, they might confuse it. So we have the theory of gravity for excellence is general relativity. I think probably all of you are familiar with the Einstein equations, the geometric side, and the source term, with the cosmological constant, which Einstein himself introduced many years ago with the hope that the universe were static, but at the end the universe was expanding. We cannot deny the successes of general relativity, and that's why we have to believe in the theory. I mean, when you are doing physics, the safest way to discover things is you start from something which is true, and then you try to derive new results. No? When your starting point is something which you are not sure about, there is an implicit danger. No, it's like propagating errors or so. So GR is safe somehow because it's successful. The gravitational waves were discovered by LIGO collaboration. It was Nobel Prize in 2017. You know perfectly when a binary system, when they rotate, they emit gravitational waves. Even our planets, when they rotate around the sun, they emit gravitational waves. But those waves are too weak to be detected. Normally these waves, which we are detecting, is because they are very intense, high frequency, violent events, etc., collision, black holes, etc. And gravitational waves is not new, actually. They were discovered indirectly in 1974. The famous Hall-Taylor prediction, which, remember, when a pulsar, a binary system is rotating, there is a rate of approaching. When they are rotating, they approach each other when they emit radiation. And that rate of decreasing of the radius is predicted by GR. And it the calculation matched with the observations, and actually that was another Nobel Prize. So gravitational waves were discovered even before, indirectly, only that we wanted to detect them directly. And that's what LIGO did. General relativity, also Einstein, the first success of GR, probably the first prediction, if you want to call it, was the precession of Mercury. All the planets describe this precession, but the Mercury is stronger. Basically, Newton said that the planets describe ellipses, but general relativity tells us that in reality it's not an ellipse, it's an ellipse which is rotating. So this is called precession, this phenomenon, and it's a consequence of GR. Additionally, GR predicts gravitational lensing, which is a powerful tool for testing dark energy and dark matter nowadays. This is also a famous prediction of Einstein, was the deviation of the lights from the sources. Basically, for example, you have a body here, and you are here. If the light comes from a source located here, it will describe curvature. Then you will believe that that source is located here. And this can be measured. It was predicted by GR, and at the end of the day, well, the famous expeditions, there were many expeditions testing it. The first one was dubious because the guy, I think he's called Eddington or so, he wanted so badly GR to be correct that people were doubting about his measures, no? The data he collected. So at the end, when another eclipse came, many expeditions went together in different points around the world, and they could measure, and this is how it was tested and proved that GR was right. Another issue is the dragging effect. When an object is rotating, the space-time is like a fluid. So, for example, you have this water and you rotate in the center, you put a ball to rotate, all the water will start to rotate also. So the space-time is the same. If you put an object here and the source is rotating, the object will have the tendency to be dragged. And this is more evident in the neighborhood of a black hole, basically. But in sources like our planet, the effect exists, but still is not so strong. Actually, I think NASA tested it. They put some satellite and they have to wait many years for detecting something. No? So, in my understanding, it has been proved also experimentally. So there are two big problems in cosmology: observational cosmology and theoretical cosmology combined. They are called dark matter and dark energy. They are different, but they are somehow connected with the content of the universe, because you will see that dark energy is almost 70% of the content of the universe, while dark matter is almost 26 of the content of the universe. So basically the majority of the universe is dark. We cannot see it. And then people are trying to conjecture or create theories for explaining the observations. The problem of dark matter started because the Newtonian theory predicts that when you go to large distances, the objects should rotate slower, because of course the gravitational attraction is smaller. No? I will put you an example: the moon. The moon, well, it's not rotating around the Earth, but let's assume it's rotating around the Earth, or a satellite. If the satellite rotates too slow, it will fall, no? If you rotate too fast, it will escape. So there is always an equilibrium. When you see objects rotating around each other in the universe, they are in an equilibrium condition. And of course, if the object is far away, they have to rotate slower for maintaining that equilibrium condition. But the problem with dark matter is that even if you go far away, the velocities don't decrease. The velocity of the objects which are far away don't decrease. And this was the first evidence of dark matter. Obviously, other evidences came. The lensing, even the CMB, etc., are evidences of dark matter. Dark energy is another issue. Dark energy, I think I will explain in the coming slides, but I don't know if I am advancing, but dark energy is an old history, actually, because it started when Einstein created the equations. He believed that the universe was static. So he introduced a cosmological constant with negative sign for keeping the universe static. But of course, a static universe is unstable, so that solution didn't make any sense. Then what happened? Hubble discovered that the universe was expanding. Then Einstein removed the cosmological constant, which is the constant you saw before. Everything nice. But in 1998, a group of scientists discovered that the universe is not only expanding, but it's also accelerating faster, and faster. what is the source of energy of that expansion? Then they call it dark energy. And the most serious candidate of dark energy is vacuum energy, because the vacuum quantum mechanically has energy. I will explain that in a moment. So, well, I call it the two biggest problems in cosmology. I don't know if it's accurate to say the biggest, but at least some of the biggest problems in cosmology. As I say, dark matter represents 30% of the content of the universe. Dark energy, I am taking here in this talk as the vacuum energy, because how do you explain the abundance? Of course, it's necessary to be 70% for keeping the flatness of observed flatness of the universe in agreement with the standard model of cosmology. So the problem of dark matter is reflected in this picture. You can see on the left-hand side, this will be a galaxy, velocity curve of a galaxy. This is velocity versus distance. So when you go far away, Newton, because at the galactic level, Newton applies. It's weak gravitational field. Newton should work. So the velocity should decrease like this. But what is happening is this. The velocity is almost flat. So it means that an object in this position moves at the same velocity or rotates at the same speed as an object closer to the source, no? Which doesn't make any sense. Now, what people do, well, they conjecture many things. They think there is dark matter, and it's a problem of particle physicists. You find dark matter. I don't care what it is, I just put it with the hand. Other people modify gravity, which in most of the cases results in a catastrophic result. As you know, every time you modify the Einstein-Hilbert action, there are ghosts, instabilities, whatever. I mean, and by Einstein-Hilbert action, I mean the action, the one usually, well, plus cosmological constant plus things. But every time you try to modify this action, disaster comes, and it's proved in massive gravity theories, in non-local theories of gravity. You will be surprised the amount of theories we have. We have Tebes, which sounds like a family name, but it's a tensor scalar vector gravity of Bekenstein and Milgrom, etc. There are huge amount of candidates everywhere. Oh, well, normally there was an animation, but it's no movie anyway. So, as I say, dark matter problem, this is a typical galaxy rotation curve. Distance from the center of the galaxy, the velocity should decrease. This is what the theory say, expected based on the visible disk, but this is what is happening in reality. So, how to explain this thing? And of course, it's not the only evidence. There are gravitational lensing. There are other issues. So, as I say a minute ago, what people do normally they introduce some additional source here, but they don't know what it is. That's why it's called dark matter. But nobody has seen dark matter, and any attempt to detect dark matter right now has been unsuccessful. So that gives us the right to try to propose whatever we want. Well, of course, not what we want, but at least consistent with what is observed. Another evidence of dark matter, as I say, is lensing. Of course, when the light cross massive objects, it deviates. And of course, if there is dark matter and it's a source of gravity, it should generate that additional deviation. In other words, you have a galaxy here. Let's put the galaxy here with all the baryonic matter. And of course, normally you would expect a curvature like this when the light, but in reality what is happening is some enhancement on the curvature perceived when the light crosses the galaxy. And the only way to enhance this angle of deviation is having an additional source of matter. So it's another evidence of dark matter. Of course, as I say a moment ago, the content of the universe requires that 70% is dark energy, 27% dark matter, and what we study normally in high school or whatever is near 5%. This comes from the Friedman, Lemaitre, and Robertson-Walker equations, blah, blah, the metric, and the standard model of cosmology. This omega is approximately 1, so our universe is supposed to be approximately flat. The CMB is another evidence of dark matter. Of course, there are serious evidences suggesting that dark matter was there. Otherwise, the galaxies cannot be formed in the period of time they are supposed to be formed, because, of course, the galaxies are created from deviations, not from the homogeneity, some seeds, and then they start to attract more matter, but for doing it faster, you need dark matter. So this is what almost everybody agrees, and this is more or less what I was saying a few minutes ago. So the problem of dark energy, now let's jump to from dark matter, dark energy here. As I say, the universe is accelerated. We had two periods of acceleration. One was inflation in principle. We have a Big Bang with a period of inflation where the universe expands quite fast. The reason is because with that expansion we can solve many problems about, for example, why the universe is homogeneous, isotropic, is in thermal equilibrium, even if it's disconnected causally. Different regions are disconnected causally. Also, the flatness problem is solved by inflation and other issues. After that, of course, there was this quark gluon plasma. The universe was too hot, the light cannot escape. But eventually the universe became colder, and then the radiation could escape, and that's the CMB. The CMB, which happens 380,000 years after the Big Bang, or 340,000 years after the Big Bang, more or less. And that's the snapshot of that moment where we perceive now with the cosmic microwave background, Planck, and these guys analyzing data with tremendous accuracy. Then after, of course, it was the period of matter dominated, where the galaxies started to form, etc. And now our universe is vacuum dominated. Most of the universe is empty, and is dominated by vacuum, in principle by vacuum energy, and is expanding accelerated. And this can be described by the Einstein equations in this form. This part you know perfectly, the Einstein tensor. This is the cosmological constant term, which now is positive in order to explain the accelerated expansion of the universe. And this is the source term, where people usually try to introduce dark matter and these kind of things. So, I mean, the most serious candidate for dark energy is vacuum energy, because the vacuum permanently creates and destroys particles, pairs of particles. Proton, antiproton, created, destroyed. Electron, positron, create and destroy. Pairs of particle, antiparticle are created, and they destroy subsequently, in consistency with the energy time uncertainty principle. Delta E, delta T. So the heavier the particle is, the less time it lives. So obviously a proton will live less, proton, antiproton will live less than an electron, positron, because it's more massive. No? And you see this in the accelerators also. When you create a particle in an accelerator, those particles have huge mass, that's why they live less. Well, because you extract them from the vacuum. They were hidden, and you could extract them from vacuum, borrow them for a moment. So there is a theoretical prediction of dark energy. They calculated, there's a way to calculate because it comes from quantum field theory. When you expand the scalar field in positive and negative frequencies, I will explain that in a moment, then you evaluate the ground state, you integrate over all the frequency modes with an ultraviolet cutoff, and you obtain this value. This K max is the maximum, let's say, frequency is related to the maximum frequency, which is related to the shortest possible scale in physics, which is the Planck length. But even with this cutoff, this value is 120 orders of magnitude larger than what we observe. So it means that this is the worst theoretical prediction in history of physics and science. And then the question comes here, is quantum field theory wrong? No, I don't think it's wrong because we use it permanently in the accelerators, etc. And it works very well. But in quantum field theory, the vacuum energy is always neglected. We don't consider it because it's just a reference point. But in gravity, the vacuum energy matters because energy is a source of gravity. So that's why it becomes a problem in gravity. Oh wait, I jumped. I think I did something bad here. Okay. Well, disappear blank. Huh? Anyway, the vacuum energy, there is serious evidence. This is not related to what we see in the universe, but it's an example that vacuum energy is a reality. The Casimir effect, when you put two parallel plates in perfect vacuum, they feel some force between each other, and that force is due to vacuum energy. And it has been tested experimentally, so it means the vacuum really has energy. There are plenty of evidences that the vacuum has energy, so that's why it's the most serious candidate for that energy, because it's abundant, it's everywhere. I mean, most of the universe is empty, right? And that energy, in that sense, if it's vacuum energy, it comes from the ground state of the quantum harmonic oscillator. Remember, when this number is 0 in the quantum harmonic oscillator, still you have energy. When you calculate that energy, what you do is to integrate all these frequencies from infrared to ultraviolet, and you obtain that catastrophic 120 orders of magnitude value larger than the experimental observations. Why the algebra? Why the quantum harmonic oscillator? Because it's the algebra we use for quantizing the quantum fields. When you go to quantum field theory, you impose canonical commutation relations in this way. Quantum field, canonical momentum, they generate. This is analogous to position and momentum in ordinary quantum mechanics. But remember that quantum mechanics is single particle approach. Quantum field theory is multi-particle approach. So they are quite different. And these commutation relations are trivial. So when you do that, of course, you obtain you recover the algebra. If you impose that algebra before, you recover the algebra of the quantum harmonic oscillator. A daga equal delta p minus p prime, etc. And of course, this is the canonical momentum, conjugate momentum. At the end of the day, the Hamiltonian is given by this guy here. When you calculate the Hamiltonian of a scalar field, for example. And if you impose this to 0, because you are in vacuum, this is a particle number, 0, you have this term, which in quantum field theory is an infinity, and you drop it. But in gravity, as I say, this is the term we calculate, and this is the term which gives you the 120 orders of magnitude of value larger than what is observed. Then how to solve this problem? How to decrease 120 orders of magnitude value coming from 0 point quantum fluctuations? Can you modify gravity? As I say, I'm not precisely afraid of modifying gravity. I work in modified gravity myself many years, and it comes like a maze in the sense that you solve one problem and you create 20 more, and then you try to cover all those problems and you create 100 more, and so on. I never finish. That's why I stopped modifying gravity for a while. I say, no, I will not do this anymore for a while because we have to think something else. This is the calculation, this is the key point. You integrate from 0 k max h bar omega. Omega is proportional to k, the weight number you solve for. This d3k, the element of volume, normally, since you integrate in spherical coordinates, people give it for granted that that element is 4 pi k squared dk, like this, because I integrate this solid angle. So it will appear a k squared here, multiplied by this case k cubed. At the end will be k4, k to the 4, which is the k to the 4 you saw before in the previous expression. So I will mention two solutions. Sorry, not so healthy these days. But I propose two possible solutions. One for dark matter and one for dark energy. Both of them have been published. Particularly the one of dark energy is, I think, undisputable. No, there is no discussion or debate that there is an issue there. The one of dark matter has been a matter of debate, more debate. But recently, more serious calculations from my side have proved that probably that's the direction. Although the initial approach I used is not completely accurate, and I will explain why. The problem for me are solved based on symmetry arguments. I mean, all the three is symmetries. I mean, symmetries in physics are important, no? Symmetries govern interactions. It is not the same. I will put you an example. Something as simple as a magnetic field. When you have a cylindrical geometry, is different to, or even an electric field. You have a sphere, or you have a line, charged line. The symmetry of the problem changes the dependence, the radial dependence of the field with respect to the radius. The radial dependence will change depending on the geometry. That's the correct way to say. So in physics, it's the same in general. We know that certain interactions obey certain symmetries, and if they don't obey those symmetries, they will behave different, completely different. In gravity, symmetries not only simplify problems, but also will tell us how the bodies, or the test bodies, behave around the source. And I think that was the key point of this approach. Let's talk a little bit about the simplest case, Schwarzschild metric. This is the Schwarzschild metric. I think everybody knows it. It's clear with the spherical symmetry clearly described here, and that's nice. If you calculate the geodesics of Schwarzschild is this mess, you can calculate with the Euler-Lagrange equations applied to the line element, and you derive this. Or you can just use the standard equation with the Christopher connection, blah, blah, blah. This is a mess. But fortunately, if you use the symmetries, it's simplified. No? At the end, it becomes something as simple. Well, it doesn't appear in this slide because this slide only shows you the symmetries. In gravity, the symmetries are represented by Killing vectors. So we have in this geometry one tiny line Killing vector, which is this. And this represents the conserved quantity associated with the Killing vector. Well, when you decrease this index, you put it down, you have to use the metric, and then this is the constant. For example, here the energy is this minus k mu, the k mu. So this minus k mu, because the index was upper, you have to put it down with the metric, and that's why this component appeared. And this is the temporal component, so it's the theta lambda. I think that there is no problem for you. I think it's quite trivial, so it's very easy for you. The angular momentum, the same. There is a Killing vector associated to the azimuthal angle, because the zenithal angle, the plane around which the object rotates arbitrary, so you don't care. You care the azimuthal angle, and the angular momentum is associated to it, so it will be r mu theta. This is the azimuthal angle, the lambda, and this part comes from the angular component of the metric, which is this part, r squared here. Okay, that's it. And theta was put 90 degrees because by standard, the standard approach always put theta fixed to 90, so that's sine of 90 is 1, and that's not a problem. This is the trivial case, and this is the equation. The equation is here. This is the equation of motion at the end. This, as simple as it. kinetic term, potential term, constant. So at the end, all the problem, and this is for massless test particle, at the end, the problem comes only to analyze the potential. So you focus on the potential, on the equilibrium conditions, and that tells you how the objects around the source move at the end of the day. And this is the standard potential, effective potential in GR, with epsilon equal 1. This is the Newtonian term. This is the centrifugal term. These two appear in Newton. This doesn't appear in Newton. This is GR contribution. It's the coupling between the angular momentum and the source term. And this term is the gift of the precession of the perihelion of Mercury. Without this term, that precession would not appear. Of course, this is the plot of the potentials. This is a standard. If you compare Newtonian gravity versus GR, you can see the differences. For example, look at these peaks here. They don't appear here, etc. So my ansatz is that it's the same ansatz which we have used in physics for a long time. Let's assume that table, you have this table. If I go inside, it looks smooth here, no? If I put this glass here or I put here, it doesn't matter, it will be the same. But if I go inside this table microscopically, it will be a mess. I will lose completely that symmetry. So the point is that depending on the scales where you are, a system can have different symmetries, describe different symmetries. So what I did is I dropped the spherically symmetric assumption at galactic scales. And I was thinking, well, let's assume that this angular term is not r squared d omega squared anymore. Well, I will put something else, such that I can reproduce the flatness of the galaxy rotation curves. And the intended results were to reproduce the Cauchy-Fisher law, which is this, to reproduce the scales of dark matter, which are these, and this was the famous modified Newtonian dynamics of Migron and Bekenstein. But there is a problem with that theory. First, it's not relativistic. It doesn't reproduce lensing. It's only a Newtonian approach. They only could reproduce galaxy rotation curves. They tried to reproduce the relativistic version of this theory, but it wasn't successful. It's called Tevez. Actually, Bekenstein used to come to Asia a few times, and I met him in Taipei 2012. He passed away already, but by then there was a famous conference, Horizons of Quantum Physics, and he was still working in that problem. Migron is another Israeli physicist. The remarkable issue of Migron is that his whole life he only worked modified Newtonian dynamics. You see all his papers are modified Newtonian dynamics. So he didn't do anything else in his career, and that's remarkable for me because, and with that he became more or less famous. And the idea of MON is that people took it serious because it could reproduce the galaxy rotation curves of many galaxies with only one parameter, which is this acceleration scale, A0. This is an interpolating function. Well, of course, if the theory is not relativistic, it makes no sense. It has to be relativistic at the end of the day. So my initial approach was to reproduce the flatness of the galaxy rotation curves. But I don't know if I show the metric here. Well, the metric, these changes come from the fact that normally the metrics are writing like this: minus 2 alpha dt squared plus beta r squared plus r squared d omega squared. Normally we give for granted this behavior here. The change I did was I changed this part by r theta d omega squared. And the reasons I did this change is because I realized that by doing this change you reproduce the flatness of the galaxy rotation curves. But it turns out that the first answer, which is what I will show now, is not perfectly a vacuum condition. And that forced me to change to find the real vacuum solution, which I found in the second paper. And the first paper was published. The second paper is almost accepted. The two papers of that energy are accepted already. One is published, the other is accepted yesterday, 2 days ago actually. But I will explain step by step. With this change, instead of this potential here, I obtain this potential, which reduces the power in the centrifugal term, so it guarantees that the Newtonian term and the centrifugal term scale in the same way, and that guarantees me that I can reproduce galaxy flatness in the galaxy rotation curves, up to some deviations due to this term. And this term becomes more important because now it scales as r squared. And this gamma is another invariant, it's not the angular momentum. Obviously, you change the angular component, the conserved quantity associated to the rotation at those scales is not the ordinary angular momentum. It's an angular momentum with respect to this metric. Still, you can call it angular momentum, but it's not the notion of angular momentum we have in mind, which is air cross momentum, for example. It will be different. Then, with those changes, I could find some interesting results. I found this equilibrium condition. When gamma squared is 2gn, these two terms cancel exactly, only remains this. And that guaranteed me that the galaxy rotation curves are approximately flat, but there is a problem, and my problem was the lensing. I mean, there was no strong force for reproducing lensing. And that problem I solved recently, looking in deeper detail the problem, and I will explain how was it. But even so, with this approach, I could find the equilibrium condition. This is the scales at which the galaxy, the dark matter effects start to appear. Is the geometric average of the gravitational radius scale R lambda. R lambda is this scale, the inverse of the acceleration of Mond, which by chance is 1 divided root square the cosmological constant. By chance. Nobody knows why the cosmological constant should appear there actually. That's a problem we don't know yet, but at least it could reproduce, and I could reproduce the Tolly Fisher law. And of course I found a potential which enhances, it gives you an effective mass which is larger than, which what my hope was that I could reproduce gravitational lensing with that, which I have not tested yet, but let's say, as I say, after a rigorous check, I found something even better. Then, of course, the new solution I found is the following. This is the metric. Actually, the Anzac metrics I was using, it was without this R actually, without this R term here. I was using this standard with this. But there is a problem. This factor R, if you don't consider it, it has to be absorbed by the time coordinate or by the R coordinate. You have to redefine the vacuum. It looks a little bit artificial. The problem came out when I tried to find the vacuum solution of this metric. I say, this is my Anzac metric with an arbitrary function here, and with this functional, and I will impose the vacuum condition. And then I found that the metric should be rather this, with this R factor here. And at the end of the day, I said, okay, what the hell, let's find the equations of motion of this. And then I found this potential. This potential, guess what? The centrifugal term dies, disappears completely because it doesn't have radial dependence. It's there, but it's that. It's a constant. The Newtonian standard Newtonian term also is replaced by this term, which is the coupling of the source term, and this is the conserved quantity associated to the rotation, and this is of course theta r. So it's inversely proportional to the radius, This means that the faster the particle rotates, more attraction it feels. It's more attractive. Okay? And this is what our matter should do. This is what our matter should do. And this extra term here is proportional to r. And it looks terrible because, of course, if you go to large distances, r, it looks like, oh no, this will blow up or something. But actually no, because very, very large distances, anyway, e squared is approximately 1. So anyway, I kept all the parameters, and when you find the equilibrium condition here, what do you get? You get this. And this is the geometric average of the gravitational radius times something. And that's something, of course, we can always impose the corresponding scale, and you reproduce the scales at which the dark matter effect should appear. So at least scaling is consistent. The scales at which dark matter appear is consistent. And in addition, with this second condition, you reproduce the Tolley-Fisher law. Of course, this gives you a compromise between the parameter theta appearing here and the constant E, which is the energy, actually, the total energy of the system. But take into account, for example, this R lambda is much larger than Ras. R lambda is like the scale of the radius of the universe. Ras is the spatial radius, or the gravitational radius, let's call it, because spatial is for black holes. And this is more larger than this, so E squared is approximately 1 anyway. Not exactly 1, but approximately 1. So I mean, this is a much more elegant result. And it gives you the scale of dark matter, which is this one. Actually, if you measure the galaxies, you go to the galaxy named Messier 33, Milky Way, Andromeda, and you calculate the geometric average between the gravitational radius and R lambda. You obtain the scale of kiloparsecs, and these are the scales where the dark matter effects are very strong. So basically match, I mean the results at least match with the observations in scale. Now about lensing, the lensing is the next paper. It's the next paper which I am working with some nice colleagues. The lensing will come from this guy here, this source term, and it will depend of eta squared. So it means if eta is big enough, if this eta is big enough, let's assume that eta is gm, for example. This will give you like gm to the cube, for example. So it will be like 66% of the galaxy is dark matter. But that dark matter is dynamical. So from my perspective, the dark matter effects are dynamical effects hidden in the Einstein equations, and this is a vacuum solution. And I haven't seen these vacuum solutions before, because probably the reason is because people were always looking into spherical symmetry. Spherical symmetry, they were thinking the whole time in that. But look that only with this small modification imposing the vacuum solution, the vacuum condition, you know the vacuum condition. Now the vacuum condition is simply saying Einstein equations equals 0. That's the vacuum condition. When you impose, because I mean, how do you derive a metric? You have to make an ansatz. You make an ansatz. And you introduce the ansatz in the Einstein equations. And then you impose the vacuum condition, and that's how you find the spatial, that's how you find the other. This is what you do. With this, I did the same, and you obtain this kind of interesting result. So this is dark matter. Let's close the chapter of dark matter. This is supposed to be dark, but I did a typo. Dark energy, I solve it, or I plan to solve it better for Nobel Schwarger, in a different way. For me, it's vacuum energy, and the problem was in the calculation. Then I did two approaches. One in static coordinates, but always when you are in static coordinates and you use the de Sitter solution, the cosmologists complain, because they say, no, the universe is Friedman, Lemaitre, Robinson, Walker. And I always explain to the cosmologists in general that those are different coordinate systems. the free millimeter Rosen walker is a comoving coordinate system. You sit in the manifold, you're a galaxy sitting in the manifold, and you move with the manifold. So you see the universe homogeneous and isotropic. But the other static coordinates, you are here and you see the manifold around you expand. But they are different ansatz. As I said, you make an ansatz, you introduce in the Einstein equations. At the end, you can find a de Sitter solution in static slides, and you can find a de Sitter solution with the free millimeter Rosen-Walker, which gives you the exponential factor, exponential da, da, da. So both solutions are equivalent. Only representations. So I worked the problem in these two different coordinate systems, and I found consistency in the results just for eliminating the doubt about, because it was always a complaint of the referees when I only use the static coordinate system. So the essential idea is that this is the de Sitter solution without matter. I wanted to see what are the effects of the cosmological constant on the angle. So I wanted to shoot down the cosmological constant here, so I did a coordinate transformation in this form. Obviously, as soon as scales, they will be negligible. And at the end, all the cosmological constant effects will be concentrated here in this C factor. Then, of course, I found the symmetry on the rotations, on the azimuthal rotations, which we saw before with the Killing vector. You remember the Killing vector, which is the 0, 0, 0, 1. Then you have the one form. In this case, it's a spherical symmetry because we are at the scales of homogeneous and isotropy. This is R squared, and the invariant would be R squared d phi d line. Technically. But of course, I did the coordinate transformation, etc. And this is the invariant in this time. C contains the effect of the cosmological constant. I integrate the azimuthal angle, and I obtain a maximal angle in a spatial coordinate, in the position space. But this is where the trick comes. You have to use the uncertainty principle because you want to map it to the momentum space. And there are quantum effects. When I use the uncertainty principle, I finish being like this. This tells me something interesting. This is telling me that K is the wave number, no? It's related to the frequency. So it means high frequency modes or short wavelength modes, they have this K very large. They don't cover so much azimuthal angle. So it means the vacuum create and destroy particles, but when they are created and destroyed, they are not looking at each other quiet, they are rotating also around each other. But it comes out when those pairs are too heavy, they don't leave enough time for covering any angle. And this is what this expression is telling me. When the pairs are, and those heavy pairs are the gas who generate the ultraviolet modes. On the other hand, the infrared modes are generated by light particles, very tiny, not so heavy, they live longer, they have more time for covering the angle. So, of course, they will contribute more to the integration. And remember that the integral is a triple integration at the end. You saw this in calculus 3, maybe. If you were engineering, calculus 3. If you were physicist, I don't know which calculus it is, because my bachelor was in engineering and the master and PhD in physics. Then, well, look at this. This is a triple integral. The zenithal angle is minus pi to pi because it's an arbitrary plane. Let's say the pairs are creating in any plane, so it doesn't matter, you have to integrate all. The trick is here in the second integration from 0 to the maximal azimuthal angle, and the cutoff remains the same, so the only change is in this second integration. But remember, this second integration corresponds to 1 over k squared. So when you integrate, the first integral will give you a factor of 2, which is irrelevant. The second integration will only put it down for the angle, the phi, 1 over k squared, a factor of 1 over k squared, which will cancel this k cubed, and it will transform into k only. And at the end, the remaining integral will scale like k squared. And this is how it's supposed to scale. I mean, this is how the experiments, when the experimental observations were done, this is how the vacuum energy density should scale at the end of the day. And of course, this publication was done in this journal. The second one is European Physical Journal C. But in the second one, well, this is the mechanism I was explaining. The pairs are created, they are rotating around each other. If they are too heavy, of course, they cannot cover so much angle after they destroy. So it means the ultraviolet modes, they are there, but simply they don't cover enough azimuth, enough angle for contributing to the vacuum energy density. So their contribution is quite irrelevant. And this suppression is due to the symmetries of the de Sitter space-time. In flat space-time, you don't have this constraint. For example, if the space-time is flat, this will not happen. And now, if you repeat the calculations, I repeated the calculations for the Friedmann-Reversor work, and you don't have to do any conversion because already all the effects of the Sitter are acting directly in the angle, in the angular component. Again, I found the constraints, I found a maximal angle, and I found that the angle, the maximal angle, behaved like an error function. Like an error function. It means in this neighborhood here is where the ultraviolet modes live. They are strongly suppressed by the error function. And only the infrared modes, which are the ones living in this region, are the survivors, let's say. So even at the Friedmann-Lemaitre-Rosen-Walker solution level, I obtain consistent results which are consistent with the static case. And I think this is what convinced the referee in the second publication. It was quite fast, huh? Anyway, well, let's say my conclusion is, it is possible to get dark matter effects without modifying gravity. All what you need is to pay attention to the symmetries at galactic scales. If you modify, I mean, there are additional vacuum solutions. There is one more vacuum solution which comes out when you modify the spherical symmetric assumption, and that vacuum solution reproduces the flatness of the galaxy rotation curves and has the potential to enhance the gravitational lensing, which that part has to be proven in a subsequent paper. But of course, that will depend from the parameter eta, the conserved quantity eta, which is equivalent to the angular momentum in that case. But it's not the angular momentum in the way how you define conventional. For that energy, we don't need to modify gravity neither. Only there are symmetry constraints for the vacuum, the 0-point quantum fluctuations, the vacuum modes. They are constrained by the symmetry of the space-time. So the ultraviolet modes are strongly suppressed, and the infrared modes are the survivors of this suppression. And that's why at the end the vacuum energy density gives you the right answer. I mean, at the end you solve the 120 orders of magnitude problem just by looking into the symmetry constraints imposed by the solution over the vacuum energy modes. Yeah, and this is my YouTube channel. If you want to follow, welcome. It's free, so you're free to follow or not. But okay, you want to take a picture, nice. It would be nice if we take a good photo at the end after the questions sessions, if there is any. Okay, this is my talk today. There were not so many interruptions. In Fudan, when I gave the talk, they asked every 5 minutes there was a question. And the talk extended like 2 hours or so, I remember. Questions, comments? Don't be shy.
What is the relation about this that you are doing with Mond?
Mond just defined the scales. I say this is not Mond. This is what confused many people when they were debating with me, because they say, well, Mond doesn't reproduce lensing. Let's put it this way: Mond MOND. It means modified Newtonian dynamics from Migron and Bekenstein. It's a Newtonian approach. It's an ansatz, let's say. It's something which these guys put with the hand without any solid theory behind. There was no theory behind. It's just they imposed one parameter and it worked nice. But then they were in desperation for finding an action, a relativistic action, modifying the Einstein reaction, blah blah. They call it Tevez. So I am not doing this modification. I am just doing the standard Einstein reaction without modifying gravity. I just focus in the changes the symmetry has to have for reproducing the observation.
Yeah,
so it's completely different.
But then you put by hand something there, right? In your metric. You just introduced something by hand.
Yeah, the ansatz, of course, has to be by hand. The ansatz, let me see, what is the match? This one.
There, yeah.
Well, this is not by hand because this is derived. Let's put, but this part, of course, this is an ansatz, metric ansatz. But as far as you can find a consistent vacuum solution, it could be valid. You respect the Einstein equations, you impose the vacuum solution, you say, how do you derive a spatial metric, for example? A spatial metric is an ansatz. You make the ansatz spherically symmetric, and you introduce them in the Einstein equations and you find the constraints, and that's how you find the spatial. So the same situation here. This is the change necessary for reproducing the flatness of the galaxy rotation field. Let's say you want to reproduce a flatness, a curve of velocity which is flat. Flat means that velocity, tangential velocity versus distance. If you want to reproduce something like this is the necessary change.
Yeah, it's just like what some people doing in phenomenology cosmology, right? You just put parameters to fit the data, but
Well, this is not precisely the, of course. It's you can say that, or of course that's why we have to do subsequent tests. No, that's why we have to see if lensing are reproduced. And we have to see if the CMB agrees with this thing. There are things to test, but of course, in that sense, if you see, yeah, this is put by hand, of course. This is by hand. And how do you get that? Well, when you find the equations of motion, the only way how the centrifugal term and the Newtonian term annihilate each other is by doing this change. So it means the symmetry at the galactic level might be modified such that the metric in the angular component behave in this way. And your question about MON is because when you find the equilibrium conditions, you find scales, the scales of dark matter, which are consistent with MON. Of course, there are some parameters you have to fix. There are certain things you have to fix because it's a little bit phenomenological, this part. But at least the scaling way, the way how it scales is consistent. Dolly Fisher, the scale of which the dark matter effects, which is, it should be at the order of kiloparsecs. If you check this calculation, this geometric average, these are the scales at which if you check measure 33 in Wikipedia or something, you will find that this scale more or less the dark matter effects appear. We knew this part. This is another scale, but this scale appears from the other approach, the previous one. This one, which I found is not a perfect vacuum solution, because the real vacuum solution is this one. Basically, I was absorbing this factor R inside the intervals of the R square before, and that was the only difference. So either you put the R in the time or R in the intervals or in the radial coordinate, or it had to be absorbed by someone. But I was thinking that's not so natural, so let's do it completely, and it came out that the real potential is this one. And this is more promising. This zeta is an arbitrary parameter actually. But this so it means the faster an object vector is around the source, the larger will be the effective mass. So it will feel more attraction, more than usual, and only for this minor change in the geometry at the end. So for me what matters, okay, you can make an answer, but if the answer doesn't turn into a vacuum solution or a consistent solution of Einstein equations, then it's meaningless. No? But as far as it comes out to be a vacuum solution and it has some consistency, then it looks promising, because anyway Einstein theory has not failed yet. The only scenario that I see in my fail is at the quantum level, of course, because we have the singularity on here. Cosmology is debatable, because if my solutions are right, it means Einstein theory is right, quantum field theory is right, only we were in the case of the energy integrating wrongly, we are doing integration wrongly. In the case of dark matter, we are taking the symmetries wrongly at the galactic scale. And if this is the case, it means GR is still right, and QFT is still right. Of course, there is physics we don't understand all the neutrinos have mass, all these kind of things we know, but at least at the most basic level, QFT and the standard model is more or less correct. That's
as far as I remember, MOND, one of the biggest problems of MOND is exactly trying to explain the bullet cluster, right? And things related to the bullet cluster.
That's right. That's where this theory stands from MOND. Because MOND, I use MOND because, at least at the most basic level, it gives you some scales. But this theory is clearly not MOND, this is GR. It's GR with some modification of the symmetries at galactic scale. But when I say, well, because anyway, MOND should be the weak fair approximation of the real theory, no? In principle. So what I demonstrated is that the results of MOND at the weak fair limit, they will appear only for GR. It's only GR has this hidden solution which nobody saw it before, and the reason why nobody saw it before probably is because people always assume spherical symmetry. It's intuition. At the cosmological level I agree, because anyway homogeneity is sort of, that's okay. At the solar system should be okay, because otherwise we don't reproduce it. But it seems that at the galactic level, this symmetry doesn't operate so well, if I'm right, no? Because of course, you know how the business of physics is, you propose something, but it could be right or wrong, but still, from my perspective, it's promising, because in addition, it's a vacuum solution.
So it's possible to consider the interaction between dark matter and the dark energy in your model.
Yeah, that's actually something which my very good colleague from Slack, I think he's in this collaboration, I have been discussing with him. He proposed precisely that we should try to analyze the interaction between dark matter and dark energy, which exists. I have seen the papers. Of course, I have to go through the phenomenology, which is tiring for a theoretical physicist, but it's true that the interaction of dark matter and dark energy is quite important. For example, because dark energy, for example, when something is trying to form, dark matter but dark energy try to destroy that structure which is going forward. And these things are measured. These guys are measuring these things.
Yeah, but as far as I remember from interacting dark energy, dark matter model, the parameters that we need to fit in even CMB data, supernova and everything, we cannot distinguish from lambda CDM. It's like tiny differences that the work to make these things interact is not worth the no results.
That's true. Yeah, until now, lambda CDM is Well, this doesn't deviate that much from lambda CDM either, actually, so it's difficult to guess. But there must be something very tiny to measure somewhere, and that's what we have to look into.
Yeah,
so that's a good comment.
The biggest challenge for me for this theoretical work is like you have to be distinguishable from the lambda CDM in some way. Otherwise, for me, makes completely no sense. If we have a much maybe more complicated or with much more parameters than lambda CDM, and you predict exactly the same thing, we have no way to distinguish between with the experiments we have. This is useless, yeah. That's papers on archive.
Exactly, that's modified reality, exactly. Well, when you modify reality, it has this problem. You introduce many parameters, but at the end, no, this is not modified reality, okay? This is GR, pure GR. There is no modification, only symmetry changes certain scales. The parameters which you see, some of them are just the constant energy, the theta appear here, but these are scales which appear in the theory anyway. A cosmological parameter and the you can call it gravitational radius for no sense spatial radius, because the spatial radius is correct when we are talking about black holes, but if there is no black hole, it's better to say gravitational radius. Yeah, because it's not an horizon necessarily. Then, but yeah, I agree that this is the tricky part. In the case of dark energy, if my solution is right, then it isn't really necessary to show an experiment, but it's true that the UV modes don't cover this angle so much, and the infrared can cover. If there's this kind of observation, would be marvelous. In the case of dark matter, I will need to see that the lensing, particularly lensing, because this theta square is related to the rotational velocity. If I can somehow link the additional observed source of matter, or dark matter, with this theta square, they match with the velocity of rotation, because it will tie the rotation pulse with the source time, no? So that's a way to falsify this approach. So there are ways to prove that this is wrong, actually. Alright, so this is what I like from this. I like to do things which people can annihilate immediately or accept. So I think these two things can be in the coming couple of years or 3, we can. But with the energy I see a little more difficult. But this one for sure is easier to falsify. This will be done in a few, maybe within the coming year or so. So, but yeah, I agree. Doing this marvelous models and then produce like a CDM, then it's like.
Can you go to the slide where you introduce this gamma instead of the angular momentum?
Okay.
I think. Yes.
Well, this was the initial answer, yeah. This gamma is the same eta, actually it's the same eta, only that this gamma eats the theta parameter. Let's say because initially when I wrote the first paper, I wrote the metric like this. I wrote the metric like -1 -2 GM -1 plus R the omega square. Then the parameter theta didn't appear here, and this gamma was obtained from this angular power. In the subsequent paper, of course, because anyways, there's solution available already. I was explaining them now that it's a stereo scale and distance square, but it's absorbed. I mean, it's like putting the speed of light to 1. Who cares, no? Sometimes you can do that. Then in the subsequent paper, this part I put theta the omega square. And instead of gamma, I define eta. But I think eta over theta is gamma or something like that. Anyway, gamma, this theta is absorbed by gamma, so it's the same as. So when you show this theta here, you show this theta here, it's exactly the same conserved quantity of this gamma. So, is the conserved quantity related to the rotation, which is the angular momentum with respect to that metric. Well, if you don't want to call it angular momentum, I accept it because it's not exactly the notion of angular momentum we have in mind, no? Which is what we usually calculate with the spherical symmetry. When spherical symmetry is expected, angular momentum conservation. Well, you get from spherical symmetry, the angular momentum in the weather unit is not conserved, it's another quantity.
If we do some metric perturbation, let's say if it is gravitational perturbation, and how about the propagation speed of the perturbation field, like radial direction or the angular direction?
I haven't evaluated it, but it would be interesting to do it. Perturbations, checking the stability, all these kind of things. It would be interesting to analyze, where I haven't done the analysis yet.
Yeah, because in GR, the propagation speed, whether it be the radial or the angular, they are all the same as the light speed. They're all.
Yeah, the speed of light, of course. Yeah, rotational rays, no?
Yeah.
I mean, it's a rotational ray, something like perturbation also, but the speed of light, yeah. I agree. Yeah, it would be interesting to do it, because still I have not involved so many people in this issue, because it was a little risky. It's a risky mission. Then I wanted to assume all full responsibility of this, and then after, of course, when it becomes more acceptable, as I told you, I'm much more convinced about the energy result. The dark matter, still you can debate things, but the fact that there is a vacuum solution by it, which you can find this way, I think is quite interesting from my side. But remember, the matrix always are ansatz. You have to make an ansatz, you have to impose the symmetries, I mean, in advance, and then you find you impose that metric in the Einstein operations and you start to solve it. That's why you have the Sitter solution for Friedmann-Lemaitre relation Walker ansatz, which is the homogeneous, and you have the Sitter metric for static coordinates also. And there is a way to make a coordinate transformation for changing from one to the other. Remember that GI is invariant with the coordinate transformation, so that's important. And when you make a coordinate transformation, you have to guarantee that the invariants don't change. I mean, the invariants have to be kept, as the name say, invariant. So this is. Any other question?
No other questions?
You can tell in Chinese if you want. I don't practice my Chinese.
So let's thank the speaker again.
Thank you. I want to ask a favor. Can we take a real photo?